Welcome back to the deep dive. Today, we are turning our attention to, well, the invisible fundamental language that powers everything you do online. Every single successful interaction, every page refresh, every order confirmation, every API call from your banking app, it's all governed by a single, really powerful set of rules. We're talking about the Hypertext Transfer Protocol, or HTTP. And while, almost everyone interacts with the web's output, the pretty pictures, the completed transactions, our goal today is to go way beneath the surface. We've put together a pretty rigorous stack of source material that's focused on breaking down HTTP from an applied, sort of strategic perspective. And our mission is simple, but I think it's ambitious: to give you the shortcut to technical fluency. We are extracting the foundational knowledge you need to instantly upgrade how you understand web performance, debug errors faster, and anticipate those big systemic reliability issues before they really escalate. This is all about turning that complex technical jargon into clear, actionable insights that, make you a better product leader or strategist.
And what's fascinating here is how often decision makers are interacting with the web's mechanics without even realizing it. They see a slow load time and they ask, why is it slow? They see a failed payment and ask, what went wrong? But without understanding HTTP, those questions they're kind of vague. But when you get the protocol, you can pinpoint whether the issue is, say, a slow server response, maybe poor caching instructions, or a really fundamental architectural error. HTTP is the how behind all the magic. And, getting fluent here lets you move from just fighting symptoms to addressing the core causes.
Okay, so let's unpack this foundational protocol. At its core, HTTP has been with us since the early 90s, and it defines the standard way systems talk to each other on the web.
Exactly. HTTP, Hypertext Transfer Protocol, is defined as the essential rule-based standard that enables all that communication. It's not the data itself. It's the structure around the data. It governs how those data packets are exchanged.
And these rules, our sources distill them down into three really essential pillars that define the interaction between any client and any server.
That's right. The first pillar dictates how a request is formally structured and made by a client. This makes sure the server always knows what the client wants. Second, it defines how a response is returned by a server, including that mandatory information like, success or failure status. And the third pillar, it sets the overall persistent rules for that communication exchange, things like timing, connection maintenance, and error handling. It's a very strict, almost diplomatic dialogue.
The ubiquity here is just staggering, and I think it's critical for you to understand that this isn't just browser stuff anymore. The whole digital world is built on these HTTP exchanges.
Oh, absolutely. I mean, think about your daily interactions. Opening a website, that's an obvious HTTP exchange. But it goes so much deeper. Submitting a detailed form, like an insurance application, that generates an HTTP request. Downloading an update for your smart home device, that's almost certainly initiated via HTTP. Even the background processes. If you use a mobile app that fetches stock market data every 5 minutes, that mobile app is functioning as an HTTP client, communicating with a back-end server using the exact same structures we're about to discuss.
So, if it's so pervasive, why should someone who's focused on, say, business outcomes or product roadmaps dedicate mental energy to its mechanics? Why do we need this fluency?
This is the core benefit of doing this deep dive. You, the learner, you're not writing the HTTP code, but you must understand its implications to make good trade-offs. For example, knowing HTTP means you can weigh the benefits of speed against the cost of data freshness, because you understand exactly what those caching headers are telling the client to do. It lets you look at a log file, that stream of cryptic numbers and letters, and immediately translate it into an operational reality. Okay, this is a user input failure, or this is a systemic infrastructure collapse. It's the shortcut to speaking fluently with your engineering partners, letting you prioritize resources based on accurate technical context rather than just, anecdotal user complaints.
So it turns a mysterious black box into a predictable engine.
Precisely. Gives you context over chaos.
To understand the conversation, we have to understand the participants and their roles. And HTTP is built entirely on this client-server model. It's a strictly sequential, one-sided dialogue that's initiated by the client.
That's a great way to put it. One-sided initiation. The client is always the initiator of the request. And it doesn't matter if that client is a web browser like Chrome, a mobile app, or even another server making an API call. The role is the same. It asks for something.
And the server, by definition, is kind of the passive partner in this dance.
Correct. The server is the host. It holds the application logic. The database is the service itself. Its job is purely reactionary. It has to receive, interpret, process the request, and then, crucially, return a response. It's a dedicated, reliable, but slightly robotic function. It only acts when it's prompted.
Okay, let's make this real. Let's walk through a scenario. Imagine a user clicking add to cart on a big e-commerce site.
Right. That simple button click kicks off this intricate multi-step process, all governed by HTTP. First, the client, your browser, or your app sends an HTTP request, and this request is carrying a very specific instruction. I want to modify resource X by adding item Y to the shopping cart that's associated with this user session.
Okay, so step two. The server gets this request. It processes it. And that could involve some pretty complex logic, right? Checking inventory, verifying the user session, updating the database.
All of that. And finally, the server sends back a response. That response is vital. It doesn't just display the item in the cart. It confirms success, hopefully with a 200 or 201 status code, which we'll get to. And it often sends back a new token or cookie to update the client state. That entire loop, initiated by the click and confirmed by the response, that is the core of the client-server interaction.
Okay, so this is where the design of the web becomes both, I think, genius and extremely difficult to manage. HTTP is inherently stateless. And I'd argue this is probably the single most important architectural feature for a product leader to really grasp.
It absolutely is. Statelessness means that by its fundamental design, each request is completely independent. When the server processes request A, it returns the response, and then it immediately forgets that the client ever existed. When request B arrives a millisecond later, the server treats it as if it were the first request ever received from a brand new client. It carries no baggage, no historical context.
But that completely flies in the face of the modern user experience. I mean, we expect the system to remember us, to keep our shopping cart, to keep us logged in for days. How can the web possibly function if the underlying mechanism has such a bad memory?
This is the core trade-off. Statelessness is a monumental feature for scalability. Imagine trying to handle billions of global users. If every single server had to maintain detailed memory for every active session, it would just become impossible. Because the server is stateless, any server can process any request at any time. This allows you to scale horizontally, just add more servers, because they're all interchangeable. This design choice is what allowed the web to handle global traffic.
So if the protocol itself is stateless, then the continuous experience we rely on, the logged-in session, the persistent cart, that must be the result of deliberate compensatory mechanisms. We're essentially building state on top of a stateless foundation.
Precisely. To compensate for HTTP's lack of memory, we have to include these explicit, deliberate mechanisms to maintain continuity. Our sources highlight a few. Cookies, which are small bits of data the server tells the client to store and send back with every request. Also, session IDs, which act as a key that the server can use to look up a stored state in a separate database. And maybe most importantly in modern APIs, tokens.
Let's drill down on tokens, specifically JWTs, which you hear about all the time. What exactly is a JSON web token, and why does it work as a state management mechanism?
So a JWT is a specific type of token, often called a signed token. What makes it so powerful is that it is self-contained. Unlike a traditional session ID, which is just a key that forces the server to go look up the user's details in a database, the JWT itself carries the necessary state metadata, like the user ID, their permissions, and when the token is going to expire.
So the token proves identity and carries all the necessary context.
Exactly. The server reads the token from the request header, it verifies its cryptographic signature to make sure it hasn't been tampered with, and instantly it has the user's context without needing an immediate database lookup. This significantly reduces server load and latency. It lets the web handle billions of independent requests while appearing to remember every single user.
That's the aha moment right there. The complexity of modern authentication is a direct tax we pay for the enormous benefit of stateless scalability. So if your team is struggling with login persistence or token expiry, the underlying tension is this mismatch between the web's stateless design and what the user demands.
It fundamentally changes how you approach debugging. If your login system is flaky, you don't blame HTTP, you look at the complexity of your state management workaround. How is the token generated, stored, and sent back in the request headers?
Now that we understand the roles client and server and the rules, like statelessness, let's get into the structure of the messages being exchanged. We need to learn to read this invisible language by decoding the request and the response.
Okay, so every request begins with the mandatory request line. This line tells the server three critical pieces of information. It's basically the I want this, doing this, using this standard.
The first is the HTTP method, the verb defining the action, like GET. And second, the resource path, so the specific destination on the server, like a PIV2 user data.
And the third mandatory piece is the HTTP version like HTTP 1.1. So if you're requesting a product with ID 123, the request line looks like Getty products 123 HTTP 1.1. And if that resource path has parameters, say you're filtering a list, those are often included right there in the path as what's called a query string, signaled by a question mark. Products.color blue and size L.
That brings up a crucial detail for the non-coder. The difference between sending data in the URL, in those query strings, versus sending it in the body. Why do we see query strings used mainly with CANT requests?
That's rooted in convention and security. CANT requests, by definition, they shouldn't change the server's state. They're just for retrieval.
Mm.
The query string is highly visible, it's logged everywhere, it shows up in your browser history, gets bookmarked. So since it's visible, it shouldn't contain sensitive or large data. Plus, query strings have size limits.
Okay, so below that critical request line are the headers. This is the metadata, the critical non-user visible context about the request itself.
Headers are indispensable. They provide the server with operational instructions. They carry authentication credentials, as we discussed, that authorization, bearer token 123 header. They define the content the client prefers to receive, like accept, application JSON. And if the request has a body, headers define its format, like content type.application JSON.
And finally, the body or the payload.
The body is the actual data container. It's optional, but if the client is sending a lot of data that needs to be processed, like all the fields of a sign-up form, that data goes into the body. Critically, because GutDT requests don't modify state, they shouldn't have a body. The body is reserved for methods that create or modify resources: POST, PUT, and PACH.
All right, so once the request is sent, the server processes it and sends back the HTTP response. The first thing it sends back is the status line, the server's report card.
The status line defines the outcome. It always contains the HTTP version, the numeric status code, which is the one we always focus on, and a brief human-readable status message. For perfect success, it's HTTP 1.1 200 OK. That code is the definitive signal.
Then we have response headers, which are metadata about the answer.
Right, and these are vital for performance and security. Response headers carry instructions like content type, which tells the browser how to interpret the body. Is it HTML, an image, or JSON? And most importantly for performance, the cache rules. These rules tell the client, hey, you just fetched this image. You don't need to ask for it again for the next 30 days. Response headers can also set cookies to maintain that session state.
And lastly, the response body, the actual answer to the request.
This is the content itself. If the request was a GET for a product page, the body contains the HTML to render that page. If it was a POST to create a new user, the body might contain the JSON representation of that new user. Even if there's an error, sometimes the body will contain a detailed error payload to help the client figure out what went wrong.
Let's talk about the HTTP methods, or the verbs. These are what give meaning to the request line. They define the specific action the client wants the server to perform, and understanding their intent is just crucial for good API design.
We really rely on 5 core methods that map almost perfectly to the Sierra operations: create, read, update, delete, which is how we manage data on the web.
Starting with the R and CRE, get.
Get is strictly for retrieval. It requests data from the server. It's by far the most common method. The fundamental property here is that it should never change the state of the server. This makes it safe, it won't cause harm, and also idempotent. Scenarios are, loading any resource, fetching a list of records, checking a status.
Okay, next, the C, post.
Post is for creation. Its purpose is to create new resources. It absolutely changes the server state. A crucial distinction here: ppost is not idempotent. Typical use cases are submitting a new customer application, processing a payment, or uploading a new file.
And then the 2 update methods, PPO and patch.
Right. PuT is the full replacement method. If you use PuT to update a user's record, the client has to send the entire updated record, replacing the old one completely. Even if you only change their name, you have to resend the email address, everything. PuT is idempotent because sending that same replacement object over and over results in the exact same final state.
And patch.
PATH is for a partial update. This method is way more efficient when you're dealing with large resources. The client only sends the specific data fields they want to modify. If a user only updates their phone number, the PATH request body only contains the new phone number. And PATH isn't required to be idempotent, though good API design often tries to make it that way.
Finally, the D in CRUD, delete.
Delete is simply the removal method. Its purpose is to remove a resource that's referenced by the resource path. A key property here: delete is considered idempotent. If the resource is gone after the first try, the next attempts just confirm that it's still gone.
We've stressed idempotence, but let's dive deeper into why this technical property, whether a request can be safely repeated, is such a fundamental decision for reliability.
This is where we bridge computer science theory with, business reliability. Idempotence is the guarantee that running an operation once or 50 times achieves the exact same final result. Get is safe, delete is safe, put is safe, as long as you always send the full, consistent resource.
But PeepSci is the danger zone. It's non-idempotent.
That's the critical distinction. If you send a non-idempotent PST request multiple times, you are creating duplicate transactions. In a world of mobile networks, flaky Wi-Fi, and aggressive client-side retries, this non-idempotent nature is the root cause of one of the most common and costly bugs out there: duplicate orders.
I hear this all the time from product people. If a user clicks place order and the UI freezes, why does the system retry and end up with two charges? Can't we just fix the retry?
The problem often isn't the retry itself, but the nature of the transaction. If that transaction uses POST, and the network connection drops after the server processes the order but before the confirmation gets back, the client assumes it failed and retries. The server has no idea the client didn't get the confirmation, so it just processes the second identical POST request, and boom, a second order is created.
So how do engineers mitigate this huge operational risk? What tool do they use to force idempotency onto a POST request?
They use a technique that brings state back into the transaction without making the server remember the client. It's called the idempotency key or a transaction ID. The client generates a unique single-use token, like a UUID, and sends it in a header with a POST request.
And what does the server do with that key?
The server gets the key and immediately checks its database. Have I seen this specific key before? If it's the first time, it processes the request, creates the order, and stores the key. If a second identical request arrives moments later with the same key, the server instantly recognizes it as a duplicate and just returns the original successful response, which prevents the creation of a second order.
That is so valuable for you to know. Understanding this lets you prioritize the engineering task. You're not just asking them to fix the bug, you're asking them to implement the idempotency key pattern for all high-value POST transactions. A perfect example of turning conceptual knowledge into a targeted improvement. All right, let's move on to status codes. They are the server's definitive statement on the outcome of a request. They're broken down into 5 categories, signaled by the first digit. We need to learn to read these as operational signals.
Right, we can pretty much skip the 1XX series, the informational ones. They relate to connection status and you almost never see them. We'll jump straight to the outcomes that really matter for product and reliability.
Okay, so 2XX means success. What are the key distinctions here?
The standard is 200 OK. Everything worked, here's your content. But 2 others are really important for API design. The 201 created code is specifically used to signal that a new resource was successfully created as a result of a POST request. The client knows not just that it worked, but that the data now exists. And the second is 204 quelv, no content. This is so important for efficiency. It signals that the request was successful, but the server is not returning any content in the body. This is often used for operations like deleting a resource or updating a status where the client doesn't need to be told anything beyond, yep, it worked. It saves bandwidth and processing time.
Okay, 3XX codes are about redirection. The resource the client asked for is somewhere else. And this is where site governance and SEO strategy collide with HTTP.
The 2 most recognized are 301 moved permanently and 302 found, which is a temporary redirect. And the distinction is profound, especially if you care about web traffic.
Right. So if a team restructures a major section of the website, say changing the path for all their product categories, why does using the correct 3XX code matter so much for the business?
It directly impacts your SEO. If you use a 301, you are telling search engines and browsers that this resource is permanently gone, and all the accumulated ranking authority, the link juice from the old URL, has to be transferred to the new one. This preserves your SEO investment. If you incorrectly use a 302, which signals a temporary change, search engines will keep checking the old URL, assuming the resource is coming back, and they won't transfer that authority. Misusing a 302 for a permanent change can effectively limb out years of SEO work. We're also seeing modern additions like 307 and 308, which are safer permanent redirects because they don't let the client change the request method on the redirect.
Okay, this next one is the critical diagnostic range for product and UX teams. The 4X range, according to our analysis, generally means the client is at fault.
That's the key diagnostic lens. The server probably got the request just fine, but it couldn't fulfill it because of something the client sent or didn't send. These errors often translate directly into UX friction or validation errors.
Let's start with the input failure. 400 bad request.
A 400 means the server received a request that was, structurally malformed or had invalid data. For example, a required field in a JSON body was missing, or a number field contained text. It tells you, we need better front-end validation, or our API documentation is probably unclear.
Moving on to access issues, 401 unauthorized versus 403 forbidden. These sound similar, but their implications are totally different.
Completely different solution pathways. 401 unauthorized means the user failed authentication. The system doesn't know who you are, your token is missing, expired, or invalid. The solution is almost always log in again. 403 forbidden means you succeeded in authenticating. The system knows exactly who you are, but your specific identity lacks the permissions to access that specific resource.
So 401 is an authentication flow problem, and 403 is a user role and permissions problem.
Exactly. If you see a spike in 403s, you need to investigate your authorization logic or maybe even look into abuse prevention.
And we can't forget the famous 404 not found.
Right, the server just cannot find the resource you requested. For a product team, high 404 rates mean the user experience is broken links, bad redirects, or resources that were deleted without proper handling. This often requires product prioritization to fix the link structure.
And finally, a strategically important one that's becoming more common, 429 too many requests.
This is vital for managing system capacity. A 429 indicates the client has sent too many requests in a given amount of time and is being rate limited. For the strategy team, this isn't necessarily a bug, it's a design choice. If you see high 429 numbers from a partner integration, it means that partner is exceeding their quota, and you need to decide whether to increase their quota, which is a business decision, or have them implement better retry logic, which is an engineering decision.
Okay, so if 4x is the client's fault, the 5x range represents the server failing to fulfill a valid request. This is the indicator of a reliability and infrastructure crisis.
A high volume of 5x errors should instantly trigger alarms and infrastructure attention.
Yeah. Start with the generic catch-all, 500 internal server error.
This means the server encountered some unexpected condition and couldn't process the request. It's often a result of an uncaught exception, a bug in the application logic, or a database query failure. It's basically the server admitting, I failed and I don't know exactly why, but it's on me.
Then we have the architecture codes, which are more common in modern distributed systems, 502 bad gateway and 503 service unavailable.
502 bad gateway is a communication error between servers. It usually means the server the client first connected to, like a load balancer, got an invalid or no response from the upstream application server. The connection between parts of your system failed. 503 service unavailable is often a capacity signal. The server is temporarily overloaded or down for maintenance. Crucially, a 503 is often a graceful failure. The system knows it's overloaded and is telling the client, please try again later. It's a mechanism to prevent total collapse.
That distinction is so important. So when we see massive traffic spikes, a well-configured system might throw 503s instead of slow 500s. Why is a 503 a better outcome?
Because a slow 500 ties up server resources, which delays every other request and can cascade into a complete failure. A fast 503 lets the server immediately reject the request and free up that resource, preserving stability for everyone else. Seeing 503s means your capacity planning is being challenged, but the system is at least failing gracefully.
And we have to cover 504 gateway timeout. This often gets confused with 503.
The distinction is the cause. A 503 signals the server is deliberately unavailable. A 504 gateway timeout means one server in the chain failed to get a timely response from an upstream server within a specific time limit. This signals a performance bottleneck or a dead process in a component behind the first contact point, not just a capacity failure. This often requires investigating slow database queries or application processing times. The ultimate strategic takeaway here is resource allocation. A 5x spike means you redirect your most expensive infrastructure engineers immediately. A 4x spike means you redirect your product and front-end teams to validation and access management. Instant classification. All right, let's talk about headers. They carry critical context without ever being seen by the user. They're the operational instructions that determine security, localization, and speed. I want to look beyond authentication and dive into their role in performance and integrity. Headers are the unsung heroes of the web. They really are. They determine key operational aspects. Let's start with performance, with caching.
Right. Performance improvements are often cheap and high impact when you get caching right. So how do response headers optimize speed?
The most direct method is the cache control, max age seconds header. When the server sends this response header with an image or a JavaScript file, it tells the client, You can store and reuse this file locally for this many seconds without asking me again.
Mm.
Okay. This bypasses network latency and server load entirely on subsequent visits. That's client-side caching.
But what if the data changes often?
Then we use what are called validation headers.
Huh.
The two key examples are etag and last modified.
How does an ETAG work?
An etag is a unique identifier, like a hash, that's assigned to a specific version of a resource. When the browser first requests it, the server sends the etag back in the response header. The next time the client needs that same resource, it sends the stored etag back in a request header called if_none_match. The server checks the etag. If the version hasn't changed, the server sends back a 304 not modified status code with no body.
So the client gets confirmation that the resource is still fresh without having to download the entire file again. That's a massive efficiency gain.
Exactly. You save bandwidth and latency by avoiding a full download. Response headers dictate this. Prioritizing setting aggressive caching headers for static content or implementing smart etag validation for changing data is a direct result of understanding this HTTP mechanism.
And beyond performance, headers are the front line of security. What key security headers should a decision maker know about?
Two really stand out. First, core headers. That's cross-origin resource sharing. These dictate which external websites are allowed to make requests to your API. If you're debugging an integration failure where one site can't fetch data from another, the issue is often a missing or wrong CORS header on the server side. Second, headers like Strict Transport Security, or HSTS, and Content Security Policy, CSP. HSTS forces the browser to only connect using HTTPS, preventing accidental unsecured connections. CSP is more complex. It prevents common attacks like cross-site scripting by restricting which sources, JavaScript, CSS, images, the browser is allowed to load and execute. If your CSP is too strict, you break functionality, too loose, and you invite vulnerabilities.
Modern digital products rely so heavily on HTTP-based APIs. We need to firmly connect all these concepts, methods, codes, headers to the API landscape.
The relationship is foundational. When we talk about REST APIs, representational state transfer, we're literally talking about using the rules of HTTP as the architectural style. REST requires using the HTTP methods get, post, put, delete directly as the operating commands for managing resources.
So that means if I, as the product designer, want to create a new resource, I have to instruct my engineers that the API contract requires a pbost request to a specific endpoint.
Correct. The elegance of REST is its adherence to HTTP conventions. The status codes also follow suit. A successful resource creation should return 201 created, not just 200 OK. The success and failure messaging is embedded right there in the protocol, which makes integrations predictable.
And what about the format of the data being exchanged in those API bodies?
JSON, JavaScript Object Notation, is overwhelmingly the standard. It's lightweight, it's structured, and it's easily parsed by pretty much every system, making it the perfect payload format for HTTP communication.
And it's important to underscore that mobile apps operate identically here. If I check my bank balance on my phone, the mobile app is just an HTTP client.
Absolutely. The mobile app constructs an HTTP request with an authorization token in the header, uses a GATE method to retrieve the balance resource, and receives a JSON response body. The underlying data flow is indistinguishable from a web browser request, which is why performance and reliability issues diagnosed via HTTP logs are universal, regardless of what the client service is.
From the listener's perspective, someone managing integrations or API roadmaps, this level of fluency just seems indispensable.
It is. Understanding HTTP lets you design robust API contracts. You can evaluate third-party integrations with a critical eye. Are they misusing methods? Are they returning appropriate status codes? If a partner API is returning a 500 when it should be a 400 because the client sent bad data, that indicates poor design and potential fragility. You can communicate clearly with your teams about method selection, avoiding ambiguity about whether an action should be a PUT or a PATCH.
Okay, we've built the theoretical foundation. Now let's synthesize this into practical strategic application across common challenges. Scenario 1. The app is slow. We need to move beyond just make it faster to diagnosing the specific HTTP bottleneck.
HTTP knowledge is your scalpel here. A slow app is a cascade of delays. First, is the slow response time localized to a few users hitting specific features? Look at the response time metric in the logs. If the delay is primarily server-side slow 5maxx responses, then the priority goes to infrastructure and application optimization, like slow database queries or inefficient code. Conversely, if the server response is fast, but the browser rendering is slow because it's reloading 50 assets every time, the bottleneck is the network. You immediately check the caching headers. Are we using cache control.maxage effectively? Is E-tag validation implemented? You shift prioritization from fixing a slow query to implementing aggressive caching, which often gives you massive wins for minimal engineering cost.
Scenario 2, caching and data freshness. This is a common trade-off conversation between product and engineering.
It is. If you're building a dashboard that shows near real-time financial data, you can't set a max age of 24 hours. You need high data freshness, which means low caching. But if you're fetching a user's profile avatar, which changes maybe once a year, you can set a max age of 1 year, and that minimizes server load significantly. Understanding HTTP headers turns this abstract discussion into a quantitative one. For this resource, we accept 60 seconds of staleness to achieve X reduction in server requests.
Okay, scenario 3, the emergence of modern HTTP versions like HTTP2 and HTTP3. How do these evolutions impact our understanding of performance optimization?
Well, while HTTP 1.1 is the grammatical foundation we've discussed, later versions were engineered specifically to combat its inefficiencies. HTTP 1.1 suffered from something called head-of-line blocking, where one slow request could hold up all subsequent requests over the same connection. HTTP 2 solved this by introducing multiplexing. It allows multiple requests and responses to be sent over a single TCP connection at the same time. For you, this means the app feels faster because the browser isn't waiting for one large image to finish before requesting the CSS file. HTTP 3 goes even further by shifting to a different underlying transport protocol, QUIC, which addresses latency and improves multiplexing even more. The takeaway is that migrating to HTTP 2 or HTTP 3 is a strategic reliability and performance initiative that directly reduces network latency for the end user.
Scenario 4, debugging integrations. Let's revisit that FormIX distinction with a partner.
Right. When an external integration fails, the engineer's first question will be about the status code. If the partner says, "We're getting a 401, the diagnosis is instant. Authentication failure. You check the request headers. If they're getting a 400 bad request or a 429 too many requests, the issue is the data they sent in the body or the frequency of their requests. Knowing the code bypasses days of back-and-forth debugging because you know exactly which part of the HTTP conversation header, body, or timing is the failure point.
Let's pull it all together into the most strategic application of this knowledge, intelligent prioritization.
This is the ultimate actionable insight. When the system is on fire, how do you decide which fire to fight first? Knowledge of 4x versus 5x codes gives you that immediate, crucial filter.
So if the error reports show a sudden widespread spike in 5x errors 500, 5022, 503, you classify this as a mass failure of the system.
Yes. This requires immediate infrastructure prioritization. It means the core engine is seizing up. The response requires the highest level of resource allocation. The SRE team, scaling initiatives, incident response. This is a problem of scaling and stability.
If, however, the report shows a high volume of 4x errors 400, 401, 404, 429, 2, you classify that as discrete failures related to user experience, validation, or access rules.
Which is a different resource allocation. These failures require attention from UX designers, front-end engineers, and product teams to fix forms, clarify error messages, or adjust API quotas. You don't pull the entire infrastructure team off the roadmap for a 400 spike, you prioritize better validation. This clarity ensures you send the right team to the right crisis, optimizing how you use resources under pressure.
So we've taken the hypertext transfer protocol, this invisible language of the web, and translated it into tactical and strategic fluency. We moved from the foundational client-server model and the tricky nature of statelessness, which necessitates complex things like JWTs, all the way through the detailed structure of requests and responses. We've unlocked the actionable implications of the HTTP verbs, especially the need to engineer around the non-idempotency of POST, and mastered the vital difference between 4MyXX client errors and 5DEX systemic server failures for prioritization. We truly hope this deep dive has transformed your understanding, moving you past just the visible output of the web and into the operational mechanics. You are now equipped to diagnose bottlenecks, weigh performance trade-offs, and communicate with surgical precision with your technical teams.
And if we connect this knowledge back to the bigger picture, you really start to see the underlying tension of the web's architecture. HTTP's stateless nature gives us unimaginable scalability and speed. But to create the persistent, personalized experiences users demand, the saved carts, the continuous sessions, we are forced to compensate with increasingly complex mechanisms like cookies and self-contained tokens stored in headers. And this raises an important question for you to think about. As products become more personal and data-intensive,
Where is the optimal line between exploiting the massive benefits of pure statelessness and accepting the necessary security and operational friction created by those complex external state management mechanisms we have to design to compensate? It is a tension that really defines modern digital product development.